Hi and welcome to this SUSECON Digital 2022 talk entitled Calico eBPF, SUSE Rancher and K3s, a perfect match. This is a technical intermediate level talk. We'll get into how SUSE Rancher with K3s is a great fit for the Calico eBPF data plane, how you can benefit from great networking performance and features with all the advantages of Rancher and K3s, and you'll even get to see a quick demo. It's a really short session. There's a lot to get into, so I'm just going to dive in. Apologies for making some assumptions along the way about pre-existing knowledge. So briefly, in an agenda, first of all, we'll just talk about how Calico eBPF is a perfect fit in a lightweight environment, which tends to be where K3s is best suited. How leveraging eBPF brings improved performance. There'll be some overlap with my other talk here, but that's fine. Then we'll move into some new content and how leveraging eBPF brings improved service handling. And finally, you'll get to see a live demo with some best practice advice about how to implement Calico eBPF with Rancher and K3s. So, in the interest of time, let's dive straight in. First of all, a little bit about me. I'm Chris Tomkins. I'm a lead developer advocate at Tigera, who are the main contributors to Project Calico. Project Calico is an open source container networking solution. I could go into a lot more detail, obviously, but in the interest of time, let's move on and make some assumptions about that. So, how can Calico eBPF fit in perfectly in a lightweight environment? Well, K3s is a great fit for a lightweight environment, and so what are the objectives in a lightweight environment? To run a software that is lightweight and doesn't consume much RAM or CPU. So eBPF is a technology that allows custom code to run inside the Linux kernel. It implements a virtual machine embedded within the Linux kernel, and thanks to an in-kernel verifier, that the code that virtual machine runs is validated from a security perspective, and also to ensure that it can't make any terrible judgments, like putting, for example, a tight loop in the Linux kernel. eBPF programs can be attached to designated code paths within the kernel, and then when those code paths are reached, the eBPF code is executed. Now, Calico uses eBPF as an optional data plane choice, which brings with it additional features, and we'll dive into what those are in a moment. So Calico is available with multiple data planes, and those are suited to different scenarios. I've done separate talks about that particular topic in much more detail, both about which data planes are suitable in which scenarios, and specifically the advantages of the eBPF data plane across lots of different environments, not just Rancher and K3s. So if you'd like to know more about that, the Tigera website and the Project Calico website has a great deal more information on all of those things. There's also information specifically about eBPF, both how it relates to Calico and how eBPF generally functions. We even have a free course available on the Tigera website. So how does eBPF relate to Calico with K3s? Calico open source is a solution for security and networking in Kubernetes, including K3s. It has a pluggable data plane. One data plane is implemented using eBPF, as I mentioned. With the eBPF data plane, Calico is even more highly performant than with the other, we'll call it the vanilla data plane, but the standard IP tables data plane. And it adds some extra nice-to-have features. The eBPF data plane brings those benefits just as effectively to a K3s deployment as to any other Kubernetes deployment. And again, our free CCOL2 eBPF course specifically covers deploying SUSE Rancher RKE cluster with eBPF and the Rancher server to manage it. We'll see a subset of that in today's demo, but if you want to dive in and do it for yourself, there's no better way. It's surprisingly easy to replace the data plane in a Calico-based Kubernetes cluster. We have 4 data planes. We have a standard Linux networking data plane, which is by far our most widely deployed data plane, and it is the most commonly deployed CNI solution for Kubernetes in clusters globally. We have the Windows host networking service, which is ideal when you have Windows-based workloads. We have the Linux eBPF data plane, which is the one we're going to see today, based on Linux eBPF kernel technology. And we have the Linux VPP data plane, which is based on the vector packet processing data plane, which brings even higher performance than the eBPF data plane in certain scenarios. If you'd like to know more about any of those data planes, I've done talks on all 4 of them, and also we have plenty of content on our website. So let's dive specifically into the Linux eBPF data plane and how it can bring additional advantages in a K3s deployment. So the first advantage is simply performance. The eBPF data plane scales to higher throughput than the standard Linux data plane, and it also uses less CPU per gigabit, which is the flip side of the same coin. Benchmarks are available at tigera.io, though I encourage you to test it yourself. Now, how does it actually bring enhanced performance? Well, the data plane code is running inside the Linux kernel, so there's no context shifting but for the code between user space and kernel space. The code paths can be more optimized because it's specific data plane code written in eBPF by our developers. The performance and feature set required can be minimal and only offer the features specifically required. And the data storage handled in eBPF maps is also minimized to specifically the data set that's required for that Kubernetes requirement. So in addition, leveraging eBPF brings improved service handling. So you get improved performance and improved service handling. You also get latency reduction, which is most noticeable with many short-lived latency-sensitive connections. You get to preserve your external source IP, you get direct server return, and you reduce complexity. Now, I'm going to dive into each one of these in more detail, with the exception of performance, which I encourage you to test yourself. Now, I've put an asterisk next to reduce complexity specifically for this K3s slide set. The reason I've done that will become clear later on when we see the live demo. But briefly speaking, you can't easily fully disable kubeproxy on K3s. What happens is kubeproxy is the technology that is implemented in a Kubernetes cluster to deliver service handling. For example, if you have a node port on your Kubernetes cluster, it's kubeproxy's job to capture that traffic coming into the nodes and to deliver it to the appropriate backend service pod. Now, because of the way that the data path works and the data plane works on a Kubernetes node, when we replace the functionality of the data plane with eBPF, we also need to rewrite kubeproxy's functionality. Now, in doing so, we actually enhanced the functionality of kubeproxy, which is why you're able to get these advanced features. But in a K3s environment, kubeproxy doesn't run as a separate pod, and therefore it can't be fully disabled. So that's why I've got the caveat around the ability to fully disable it. So let's see an explanation of how we get direct server return and source IP preservation. And I'll explain what both of those are in more detail as we get into the slides for that. So first of all, we see what K3s service handling looks like with kubeproxy. Now, bear in mind, this is without the eBPF data plane. So this is for a standard Calico IP tables data plane, or for most other data planes for Kubernetes. Now, just to describe what we have in this diagram, we have the external client up here, which could be an actual user, or it could be a client of an API, so a programmatic client of an API that's running in your Kubernetes cluster. At the bottom of the diagram, we have the Kubernetes cluster with 2 nodes. Obviously, that could be any number of nodes. And we have a service pod, which actually is providing the service that the end user actually wants to utilize. We have kubeproxy, which is in the orange box here, and its job is to, as mentioned, to implement service handling. So it captures the service request when the external client makes it. So let's talk through how this works without the eBPF data plane first. So step one, the external client makes a connection, and some kind of external process in the network ensures that the connection ends up on one of the Kubernetes nodes. In the case of this diagram, I've shown that with the service handling happening on another node that's different to the one that's hosting the service pod. Of course, depending on a random roll of the dice, it could be that the service pod is actually on the same workload, same node, excuse me. So the first thing that kubeproxy does is it both DNATs, that's destination network address translation, and SNAT, source network address translation, on that traffic. It replaces the source IP of the traffic request with its own IP, and the destination IP with the pod IP of the service pod. Now, let's talk about the destination NAT first. That's a necessary step because the traffic has to find its way to the service pod, and the service pod has to realize that the traffic is intended for it. So that's why the destination NAT happens. The source NAT, though, the reason for it is not so obvious. The reason is that the traffic needs to pass back through kubeproxy, and in order for this connection tracking to be handled correctly. And that means that kubeproxy needs to see both the ingress and egress parts of the flow. So to ensure that the traffic passes back through, it also source NATs it, which means that after the service pod is finished talking, it passes the traffic back, and kubeproxy handles it. So step 2, the packet's forwarded to the service pod. Step 3, the pod sees the ingress node as the source. Note that the service pod never gets to see the real IP of the external client. It just sees the request coming from the kubeproxy on the other node. Now that can be a big problem depending on your scenario. You might have a compliance requirement or a logging requirement, or you might find it difficult to achieve good visibility for your application teams if they can't see the real IP address of the external client. So that functionality is going to get fixed by adding the eBPF data plane in a moment. Then as the traffic returns, the source and destination NATs are reversed. Notice that the traffic also goes back through the ingress node. So let's see how that looks now with the eBPF data plane turned on. The first thing you'll notice is we've still got the external client and the 2 Kubernetes nodes, but we don't have kubeproxy anymore. As I said, in a K3s environment, it's not possible to entirely turn off kubeproxy, but it is possible to take it out of the data path, which is what we've done. The first thing that happens is the BPF program spots, so the traffic ingresses as usual. The BPF program on the ingress node spots that the packet is destined to the service. It makes a load balancing decision, and it sends the packet to the node hosting the pod. It does not need to do any network address translation. It is able to pass that down, essentially pass it down a pipe, as it were, and get it onto the destination Kubernetes node. Then the BPF program does a destination NAT, so that no source NAT address translation happens, but a destination NAT does. So why do we still need the destination NAT? Well, that's simply because the service pod won't accept the traffic if it doesn't recognize it as being for itself. So a destination NAT is unavoidable. That's a necessary step, no matter how you implement the data plane. The pod sees the real source IP. So if you have, like I said, if you have a compliance requirement, a logging requirement, or maybe you'd like to blacklist certain geo IPs, something like that, this having the eBPF data plane in your K3s clusters solves that problem for you. Then the pod responds. The BPF program reverses the DNAT, and the traffic goes straight out to the external client. So that's the other advantage I mentioned earlier, direct server return. If the network is configured to allow it, the packet returns directly to the external client, meaning that there's no network load put on the for the egress put on the ingress node, and there's slightly reduced latency. If your upstream network does not allow direct server return, because that can sometimes appear as a vulnerability or an attack to your upstream network. So depending on the configuration of your upstream network, it's possible to configure the eBPF data plane to respond through the ingress node. So having seen these diagrams, if we just look at the benefits again of using eBPF on your K3s clusters, the first one is performance, and then latency reduction, preserving source IPs, and direct server return, and arguably reduced complexity depending on how you look at that. So let's see a live demo with some comments about best practices. Now, I want to say first of all that this live demo is adapted from the free Calico eBPF course that we offer at the Project Calico website. So if you go to the Project Calico or Tigera website, you'll find the free Calico eBPF course there. And it not only teaches you specifically about Calico eBPF, but also a little about eBPF more generally. So it's a great learning resource. The version of this lab in the course is a longer version, which is in much more detail. So if this is interesting to you, please feel free to sign up for that course. And you don't even necessarily have to complete the course, although of course I'd encourage you to do so. But if you'd just like to start the course to get access to the lab, that's also possible. So what's the demo going to look like? It's adapted from our course, as I said. It's a real live demo, but it has been accelerated. So because we go through some steps that require waiting, what I've done is just a few minutes ago, I did the live demo. I used a terminal recording application to record the demo, and I'm just accelerated it. So I'll be playing it back to you. But it was a live demo. I just did it a few moments ago. What we'll do is build an RKE cluster with no Kubernetes CNI. Then we'll do that on Google's GCP platform, although it would be equally possible anywhere else. We'll install the latest version of Calico open source on the cluster, which is the CNI from Calico, and that will be installed with the default data plane, which is not at this time the eBPF data plane. Then we'll switch the cluster to the eBPF data plane, and that will be the end of the demo. If you want to try it yourself, including actually seeing workloads running, because we're going to run out of time, I'll have to keep this quite quick. You can do you can either use the cluster.yaml that I'm about to use, which is linked there, or you can dive straight into that course and follow it through. Now, I should say there are some prerequisites for being able to run run Calico eBPF on your K3s cluster. You can find those listed on the Project Calico website, but broadly speaking, there are some prerequisites around what you have installed. So for example, you need an up-to-date kernel version, and there are also some caveats around the feature set that's available. So for example, the eBPF data plane doesn't support IPv6 at this moment in time. So with that said, let's dive in. So here we have a terminal, and as you can see, I'm just kicking off my recording, which was recorded just a few minutes ago. So the first thing I do is change folder and jump into this folder where I'm going to work. And then I list off the virtual machines. So I use the command gcloud compute instances list, and that's a Google Cloud command, and I filter based on this prefix. And I can see the 4 nodes that I've built, a control node and 3 worker nodes. They've got 4 external IPs there, which are ephemeral. Those change every time you build. So what I've done, if you choose to follow along with me, what I've done then is taken those 4 IPs and I've substituted them into the cluster.yaml file. So this is the same cluster.yaml file that I linked to a moment ago in the slides, but I've substituted in those IPs, as you can see here. I'll let you go and examine that file yourself on the web if you want to do so. But what I've really done is I've customized it so that it won't have a CNI at all. Next thing is I run RKE up, which takes that cluster.yaml and applies it to the 4 nodes. So we'll let that run for a second. Now, like I said, this has been slightly accelerated, so it probably takes roughly twice as long to complete this step without the acceleration. So if you choose to go along, then you can expect it to take slightly longer. While it's doing that, I'll tell you what we're going to do after this has completed. The first thing is that I mentioned that we don't use kubeproxy when we're running the eBPF data plane. Now, when a component in Kubernetes wants to talk to the Kubernetes API, usually that happens through kubeproxy. So we've got a catch-22 situation. Calico wants to talk to the Kubernetes API in order to get to exchange the data it needs to do, but it would usually do that through kubeproxy. It can't do that because it's going to replace kubeproxy's functionality. So the first thing we'll do when this finishes is to actually reconfigure Calico to talk directly to the actual pod endpoint rather than a Kubernetes endpoint rather than to the service hosted by kubeproxy. Once we've done that, we'll disable. Just pausing that. I was trying to watch it to make sure I paused it at the right moment. Well, let's actually do that first step, and then I'll tell you what comes next. So we've finished building the Kubernetes cluster. Let's examine it. So we just quickly export the kube config so that we're able to connect to the cluster, and then we run get nodes and get pods in all namespaces just to check the health of the cluster. You can see we've got the 4 nodes, nice and up to date, and you can see that RKE has completed the deploy jobs, but you can see that these are in a container creating state, and that's because the cluster is nodes are in a not ready state. And the reason is because there is not yet any CNI, no container networking on this cluster, so we need to put CNI in place. So what we're going to do now is, I should have said this before I told you about telling Calico to talk directly to the API. The first step actually is to put Calico on the cluster. So I use wget to get 2 default manifests for the Tigera operator, which is the component from Tigera that's responsible for deploying Calico on a new cluster, and custom resources.yaml, which tells the Tigera operator what the configuration should look like. I only make one change to that file using sed, and I just replace some IP addressing to match what I'm using in the cluster. The next thing is I use kubecut or create, and I apply both of those manifests to the cluster. The first one is applying the Tigera operator to the cluster, and the second one is giving the operator a configuration for Calico to tell it to reach that target state. So those 2 get pushed out onto the cluster. And if I examine it again, you'll see that now the cluster is ready, and it's got Calico running on all, as a daemon set. So each Kubernetes node has a Calico node 2. You have Calico Typha, which is the fan-out scaling daemon. Much more information about that on our website because we're running low on time. And you've got Calico kube controllers and the Tigera operator. All right, so it's that simple to put Calico on the cluster, but we haven't enabled eBPF yet. So to do that, we grab the Kubernetes endpoint as I described, and then we create a config map in the Tigera operator namespace. And what we're doing is we're passing the details that we discovered here of where the real endpoint for the Kubernetes API is. We're passing those as a config map to the Tigera operator, which will reconfigure Calico appropriately to talk directly to the API. So we apply that, and you'll see that if we examine the pods again, you'll see that instantly the Calico nodes restart. They do that instantaneously to take on that new config. Right, the next step is that I told you that with K3s we can't fully disable kubeproxy as we would usually wish to. So you can see that if we go back up here, there's no kubeproxy appearing to run, and that's because it's running as part of one of the other processes. So what we do is instead of disabling kubeproxy, we tell Calico Felix, which is the per node agent that runs on each node, we tell it to not tried to tidy up the IP tables rules because we don't want kubeproxy to keep trying to reinstantiate the rules and Calico Felix to keep trying to remove them. So we just tell Calico to allow kubeproxy to leave those rules in place. They won't get used anyway because the eBPF data plane won't be processing the IP tables rules. So then all we have to do after that is to issue this command to patch the installation resource, specifying that Linux data plane should be BPF. We do so, and if we examine the pods again, we can see that they're restarting yet again instantaneously to run eBPF. Any sessions that are actually in flow at that time will actually continue to work on the IP tables data plane until they are aged out naturally, and then when they reconnect, they'll connect in eBPF. So it's quite graceful. And then I've just run the command again to show you that indeed Calico nodes have all restarted. And that's it. So like I said, there's a much better, deeper version of that demo, and I really encourage you to dive into the course and see that. That's all we have time for. I'm out of time already. I'm very conscious that was a really quick session. I tried to get through a lot of material. So if you're interested in much more information about eBPF, much more information about Calico's data planes, about deploying Calico with K3s, or training courses on anything from basic Kubernetes networking to specifics about eBPF, all of those resources are available on the Project Calico or Tigera websites. And I'm available. My name's Chris Tomkins. I'm available on both the Calico users Slack. I'll be available through the SUSECON channels and through the usual channels, LinkedIn and so on. I make it my mission to be very reachable. So I'd love to speak to you if you have any questions or comments, or if you'd like to dive into more detail. Thank you so much for attending my session. I hope you found it useful.